Okay, so what if all the weirdness of quantum mechanics, particles being in two places at once, those spooky connections across galaxies, what if it isn't weird at all? What if it's just a shadow? A shadow of a deeper, hidden reality that has a surprisingly beautiful geometric shape. Well, a groundbreaking new paper suggests just that. And today, we're going to break down its wild argument that our universe is, fundamentally, a fractal.
Here's how we're going to do it. First, we'll tackle the central problem that has had physicists scratching their heads for a century. Then, we'll look at 4 spooky quantum clues that point towards a solution. After that, we'll explore the wild idea that our brains are actually filtering this deeper reality out. Then comes the big reveal, this new fractal geometry. And finally, we'll see how we might actually build a sensor to see it for ourselves. Let's dive in.
So, here's the big question, right? How is it possible that there are 2 completely different sets of rules for reality? The world we see every day, the classical world of baseballs and planets, it follows predictable, common-sense rules. But the quantum world that everything is built on, that follows a totally different script, one that's all about probability, bizarre connections, and things that just seem to defy logic. How can both of these be true at the same time?
All right, so let's properly kick things off with what's known as the quantum reality problem. This is the fundamental tension, the big paradox, that this new way of thinking is trying to solve. The authors of this paper suggest that the quantum world we measure is really just a projection, kind of a shadow of a much richer, higher-dimensional reality they call a hyperspace. Think of it like this. There's a hidden reality we can't see directly, but we can see its effects rippling into our world. It's kind of like Plato's cave allegory. We're all just staring at shadows on a wall, totally unaware of the real objects casting them.
So, if we're only seeing shadows, what clues do we have that point to this deeper reality? Well, the paper zeroes in on 4 key spooky hallmarks of quantum mechanics. You can think of these as the fingerprints left behind by this hidden hyperspace.
First up, we've got superposition. This is the famous, mind-bending idea that a quantum particle can literally be in multiple states at once. The classic way to think about it is a spinning coin. While it's in the air, it's not heads and it's not tails. It's in a fuzzy, probabilistic state of being both. It's only when we measure it, when that coin finally lands, that it's forced to collapse into one single definite state.
And you can actually see the proof right here on this chart. That dashed orange line, that's what classical physics predicts we should see. But the solid blue line, with those distinct peaks and valleys, that's what we actually measure in experiments. That wavy interference pattern is the absolute smoking gun for superposition, a clear signal of something happening beyond our normal, classical world.
Okay, next up is entanglement, the one Einstein famously called spooky action at a distance. This is where 2 particles can become so deeply linked that their fates are completely intertwined. If you measure a property of one particle, you instantly influence the other one, even if they're separated by billions of light years. It's a connection that seems to defy the cosmic speed limit.
And this chart just shows you how spooky it really is. That blue line is tracking the correlation between 2 entangled particles. Now, classical physics has a hard limit, a speed limit, on how correlated 2 separate things can be. That's the dashed gray line. But as you can see, the quantum correlations measured in experiments just smash right through that classical ceiling. It's proof of a connection that our everyday physics just can't explain.
Our third hallmark is something called retroactiveness. And this one is a real mind-bender. In our world, right, if you check your car's tire pressure and then you check the fuel gauge, you get the exact same information as if you checked the fuel first. The order doesn't matter. But in the quantum world, oh man, the sequence of your measurements can fundamentally change the reality of what you're measuring.
And look, this slide shows you just how real this effect is. You start with a particle in a known state. If you decide to measure property X first and then property Z, the result you get for Z is totally random, a 50-50 shot. But if you take the exact same particle and measure Z first and then X, the result for Z is 100% certain every single time. The only thing that changed was the order you looked.
And our fourth and final hallmark is tunneling. Classically, this is just impossible. If you roll a ball out a hill and it doesn't have enough energy to get to the top, it will never ever get to the other side. But quantum particles, they play by different rules. They have a real non-zero probability of just appearing on the other side of a barrier as if they've tunneled straight through it like a ghost walking through a wall. And here's kind of how it works. That blue line represents the particle's wave function, basically the probability of finding it somewhere. As it hits the barrier, that gray block, it doesn't just bounce off. A tiny piece of that wave actually leaks through and pops out on the other side. This means there's a real, measurable chance the particle will be found where it has no business being. It's a direct violation of classical logic.
So, if the universe is built on all this strangeness, if superposition and entanglement are happening all around us all the time, then why don't we see it? Why does the world feel so solid and predictable? Well, this brings us to a really fascinating part of the paper's argument: our brain's classical filter. The idea is that the reason our world seems normal is because our brains are actively editing out all the quantum weirdness.
This slide really puts it into perspective. On the left, you've got the underlying quantum reality. It's complex, it's probabilistic, and it's just swimming in information. But on the right, you've got the reality our brain actually constructs for us, the one you're living in right now. It's a simplified, predictable model based on things like linear cause and effect. Our brain takes that impossibly rich quantum signal and compresses it way down into a reality that's much easier to navigate and survive it. So why does this filtering happen? The paper points to two main reasons. First, something called decoherence. You see, quantum effects are just unbelievably fast and fragile. They fade away trillions of times faster than our neurons can even fire. So by the time any signal even has a chance to reach our brain, the quantum weirdness is already gone. And second, there's compressibility. Our brains evolved to be pattern-finding machines. They're wired to look for simple, repeatable patterns, cause and effect, cycles, things that make sense. Anything that doesn't fit that simple mold, our brain just tends to dismiss as random noise.
Okay, so if our brains are filtering out a deeper reality, then what is the shape of that reality? What are we missing? This right here is the absolute core of the paper, the big reveal, a new fractal geometry. The authors argue that this hidden hyperspace that we're blind to has a very specific and very surprising mathematical structure.
And this graph reveals that structure. What you're looking at, that blue line, is how the complexity, or the dimension, of this quantum hyperspace grows. See how it's not a straight line? So it's not linear. And it's not rocketing straight up, so it's not exponential either. It follows this very unique curve that's somewhere in between. And that specific growth pattern, as the paper proves, is the telltale signature of a fractal. And they even calculated its dimension, about 1.47. Now think about that. That's not a whole number. It's not 1D like a line or 2D like a flat surface. A fractional dimension like this is literally the mathematical definition of a fractal. It's a complex, intricate object that exists between our normal, familiar dimensions. So what does that actually mean? Well, this visual gives you the idea. A fractal is a self-similar shape, which means the same patterns repeat over and over again at smaller and smaller scales. Think about a fern leaf or a snowflake or even a coastline on a map. As you zoom in, you just keep seeing the same basic structures appear again and again. The argument here is that the hidden fabric of our quantum reality is built exactly like that. But here's where it gets really exciting. This isn't just some abstract mathematical idea. Maybe the most incredible part of this work is that it actually proposes a way to detect this hidden geometry. So let's look at the plan for actually building a device for sensing the hyperspace. And this is the blueprint for it. The paper calls it a polyatomic time crystal manifold, or PTC6 for short. Now that's a mouthful, but you can basically think of it as a special network of tiny, perfectly synchronized oscillators or clocks. The whole network is specifically designed, using some really cool number theory, to resonate with the underlying fractal geometry of that hidden hyperspace. It's tuned to listen to the fractal's frequency. And here it is. This is the incredible payoff. That red line represents a tiny theoretical disturbance, a ripple, in that hidden hyperspace we can't see. And the blue line? That is the measured collective response from the PTC6 sensor. Just look at that. It perfectly mirrors the hidden signal. This is the proof of concept, showing that this network could act as a universal sensor, turning an invisible geometric event into a real macroscopic signal that we can actually measure. And this brings us to our final mind-expanding thought. This idea doesn't just offer a new explanation for quantum mechanics. It gives us a potential blueprint for a device to listen in on the deep structure of reality itself. So, the question it leaves us with is this. If we can finally build a sensor to perceive this hidden geometry, what else have we been missing? What else is hiding out there in the fractal?